Hydroelectric power plant. In a hydroelectric power plant, electricity is produced from water. A dam is built across a large river to hold back the river water and raise its level to form a reservoir. At the bottom of the dam, there is a floodgate. Water flows through the penstock and rotates the turbine. The flowing water rotates the turbine, which is placed at the end of the penstock. The turbine, in turn, rotates the shaft that is connected to the coils of a generator. These coils are placed in between strong magnetic poles. The rotating shaft turns the coil.
Earlier, we saw how an outside force can break an electron away from an atom and start an electron chain reaction, an electric current flow. One way to provide that outside force is by use of a magnet. It was proved with iron filings that a magnet has magnetic lines of force which connect its poles. For simplicity, let's consider the effect of this magnetic field on a single electrically neutral atom. Now, we move the magnet so that the magnetic field strikes the atom, supplying energy which forces an electron to leave its atom and become a free electron. The result is a sort of electron chain reaction. In a substance such as a length of wire, electrons are normally moving in all directions. But when a magnetic field is passed through the wire, several electrons are forced from their atoms and move in one direction. Now, in studying electricity, we're mainly interested in the movement of free electrons. So, for convenience, we'll look only at the action of electrons in the wire. When the magnetic field sweeps down across the wire, electrons move in one direction. When the magnetic field sweeps up across the wire, the electrons move in the opposite direction.
Particles can have a positive charge or a negative charge. Particles with the same charge repel one another. Particles with opposite charges attract one another. This is because charged particles create electric fields. And electric fields exert a force on charged particles. When there is an electric field between 2 points, we say that there is a voltage between them. Voltage can be thought of as the height of a mountain. Rocks at higher elevations can do more damage. The same is true with voltage. The height of the mountain tells you the energy of each falling rock. The total power is the height of the mountain times the number of falling rocks. Similarly, the voltage is the energy of each charged particle. The total power is the voltage times the number of particles. The number of particles is called the current. In a circuit, the charged particles flow through wires. If the wire is cut, the current stops flowing.
In a previous video, I said that a resistor is a component that limits current. It limits the flow of charge. Ohm's law is one of the most important laws in all of electronics. It relates current, voltage, and resistance. With Ohm's law, you can do a lot of simple circuit design and analysis.
This video is about electrical energy and power. Now, for the most part, I just want you to be able to use and understand the equation for power, which I'm going to give to you right now. Power, electrical power, is equal to the voltage across something times the current that's going through that thing.
This is an introduction to the importance of electromagnetic induction. If you ever drove a car, you will know the motor of an engine relies on all sorts of fields, one being the magnetic field, which in fact rotates the coil itself. The engineering behind this motor is heavily reliant on magnetic fields and currents. In fact, all substances respond to the magnetic field, even us. Magnetic fields also give rise to currents, which we can predict the direction of using Fleming's left-hand rule. Our first finger being the magnetic field, our second finger being the current, and our thumb being the thrust, the motive force. So how does a coil rotate in an engine? Here's a brief example, but with a wire instead. If we were to take a wire which has a magnetic field going into the plane, which can be seen by the small crosshairs, and we were to physically move that wire downwards, then a current will flow to such as to oppose that force. In other words, a current will flow that will tend to cause the wire to go in the other direction to oppose the force that's causing the current in the first place. Which means if you use the left-hand rule, you've got the force going upwards, the resistive force, and the field going inwards, which will mean the current will flow to the right, as you can see. But suppose it didn't work like that. Well, we'd have an infinite motion, a phenomenon which just isn't possible. Why, you say? Let's say the current moves to the left, reinforcing the force instead of opposing it. Then we would jerk the wire downwards. A current will flow to jerk the wire down even more, which in turn will cause a greater current, which will make the wire move down even more, which will produce an even greater current, which will cause the wire to move down even more, until there is a never-ending occurrence. Hence, an old chap called Heinrich Lenz deduced that this cannot be the case, giving rise to Lenz's law.
Second motor, it's not getting power, okay, actually gets some voltage. So if I put the voltage thing on here, it's hard to hold the camera, put the voltage thing on here at the same time, you'll see so you see the motor's getting driven, right? So both gears are spinning, right? The one on the left is actually the one that's being powered, and the one on the right doesn't have any power. I've just got these two indicators on there. And if I move over here, you can see that there's some voltage. It's not 5 volts, it's almost 1 volt, but that's power that's being generated by the second motor. So just turning that second motor is actually generating power. So you can actually generate power. You can generate power just by turning any electric motor. Will generate power to the leads. Okay, so that's how a generator works.